Hi, I want to talk about the problem of trying to wheel yourself if you happen to be in a wheelchair from the ground up onto a curb without the benefit of a ramp. Now, this is an example of a static equilibrium problem. So right at the point where you're about to lift yourself up, all of the forces acting on you would have to be equal to zero, the torques acting on you would have to be equal to zero, and you would be able to supply a force pushing on the wheel sufficient to be able to roll yourself up and over a curb. So here I have about a quarter of a wheelchair wheel, which typically has a radius of around 30 centimeters. Now, where you would be pushing would be way above the board. I didn't have enough room to draw it, but ideally you'd push from the top directly parallel to the ground. Now there are a lot of ways you could go about calculating torque, because if the torques sum to zero around one axis of rotation, they sum to zero around all axes of rotation. But the place where you're really going to want to do that is right at where the edge of the wheel meets the curb. Because if you're lifting yourself up and off the ground, well, you have to be pushing forward, but the ground doesn't need to be supporting you upward. There'd be no normal force here at the bottom of the wheel. It's just the curb that would be supplying any normal force, pushing back against your forward push, but also pushing up in response to your weight. So let's say that the center of mass of everyone is centered right above the axle of the wheel of the wheelchair, which kind of makes sense because in order to actually get up onto a curb, you'd have to pop a wheelie first in order to be able to do that. Now once you make contact there, you get a little bit of leeway between where your center of mass has to be and the point of contact on the ground, but let's make our lives simple and take a look at the case where you happen to be directly over the axle of that wheel. Now, if I were to take a look at the forces to calculate torques, any force at that point right there contributes no torque. There's no normal force there, so there's no torque there to deal with. We would just have the weight, which I said is acting on a line that passes through the axle, and we have the pushing force up at the top of the wheel. That's it. Those are the only two forces that are providing torques. That push forward is giving you a clockwise torque, and your weight in this scenario would be giving you a counterclockwise torque. So let's calculate those torques, but let's do it from the perspective of finding a lever arm. So the lever arm is the closest distance that that force would act from your center of rotation. So for your weight, if it's acting on a line passing through an axle, that's going to be equal to this distance d from where the bottom edge of the wheel makes contact with the ground and where the wheel makes contact with the curb. For your push up here, the lever arm is going to be from where we make contact with the curb up to the top of the wheel. So in terms of lever arms, the force that you supply is a little bit easier. It's just going to be the diameter of the wheel, 2 times the radius, minus the height of the curb. For figuring out this distance here, we need to take a look at a little bit of trigonometry, because my distance d forms a right triangle where the two sides that make up my 90-degree angle are my distance d, and this distance, the radius of the wheel minus the height of the curb. So, using Pythagoras Theorem, that distance squared plus the radius minus the height of the curb squared is going to equal my hypotenuse, which is just the radius of the wheel squared. So, when I FOIL this out, I have r squared minus 2 times r times h plus h squared. So an r squared on each side cancels out, and d squared would have to be equal to 2 times r times h, or h times r, minus h squared. Or my lever arm distance d would be the square root of 2 times the height of the curb times the radius of the wheelchair wheel minus the height of the curb squared. Now our torques, the torque for the weight is equal to whatever weight we're dealing with times that lever arm d we just calculated. And the torque provided by our force is just going to be the total pushing force we have at the top of the wheel times our lever arm for that force of 2 times the radius minus h. So if I set my two torques equal to each other, because opposing directions, static equilibrium, the force that you'd have to supply would be the weight that you're trying to push up and over that curb times the lever arm distance for the weight, the square root of 2 times the height of the curb times the radius of the wheelchair minus the height of the curb squared, divided by the lever arm for the pushing force, the diameter minus the height of the curb. So I mentioned a few numbers. Wheelchairs, as I said earlier, have a typical radius of about 30 centimeters, 0.3 meters. A person and a wheelchair usually tend to weigh a bit more than you think. You may not have much experience with wheelchairs. They usually tend to be pretty heavy. So here I said the weight was 1,600 newtons. That probably means that the person has a mass of probably somewhere on the order of 120 kilograms plus the mass of the wheelchair that we have to deal with. Now, typically wheelchairs have 2 wheels. So what you could do is each wheel would require a force. The total force would have to be able to be enough to lift our total weight. So let's assume that each arm can push equally. So each arm would have to be responsible for 800 newtons of weight. And I said the curb height is 6 inches. The reason why I chose 6 inches is because that is the maximum height of a curb according to the Americans with Disabilities Act, where you don't need to provide a ramp for someone in a wheelchair. 6 inches is 15.24 centimeters, which is the distance from the bottom of my screen up to this mark here, or about an inch longer than one of the markers that I'm dealing with. That's pretty high. Now in terms of force, if I take 800 newtons, multiply by this distance d here, divided by, well, 0.6 minus 0.15 is going to be about 0.45 meters, I end up with a necessary force from each hand of 470 newtons. And that means your total pushing force would have to be 940 newtons. Or, to put it another way, 47/80ths, that's a little bit under 70%. So you would have to be able to push forward with 70% of not just your body weight, but the weight of a wheelchair. Once you've popped the wheelie, to be able to get the larger wheel in contact with the curb in order to push yourself up and over the worst possible ADA compliant curb. And that sounds not very fun at all. Thanks for watching.